All right, so today we are not gonna cover anything new. I just want to go over with you maybe quickly the guide for your upcoming test number 1. So I confirm all the details in the guide this morning, but the information mentioned in the guide is just consistent with what we said earlier in the class on Monday and Wednesday. So nothing new really, just a little bit more details. But I can go over that very quickly, some highlights. And then we can take a look at maybe the solution for your assignment number 1, right? And then I can just give you some highlights about individual question there very quickly. But if you got any more like a specific question, you can also ask. I can see if I can help right here. Okay, we'll see. All right. But it's very important for you to really look at the solution there. As for the programming part, you really want to make sure you can do it on your own. I'm going to show you the steps and what will be the expectation. I can highlight it about something you should really pay attention to, the programming part. And for the written part, you also have to make sure, definitely want to know how to trace the depth first search, like what we put in the solution. And also you want to be able to do proofs as well, right? You can also go over the proof. I also put a detailed proof there as well. We can do some highlights. Okay, let's now start with right here, just very quickly. This one I don't want to take too long because you guys can also read it right here. Okay, so let me put it here. All right, so the guide, excuse me. So the guide for your test 1 is already on the E-class. Right, let me also keep track of the time right here. Okay. So the guide right here, okay, here, very quickly. So it's going to be Monday, and then 50 minutes, and 4:30 to 5:20, and then it's going to be Williams Sports Center, 106 and 108. So me and the TAs, we will be there. So please just wait outside when you arrive, and then we're going to let you in as soon as we are set with the room. You can feel free to bring your own sketch paper. We don't have sketch paper for you. Just make sure it's blank. You can bring as many as you like. Okay. And make sure you bring your mobile phone because you're going to need it for the dual mobile verification for E-class. So it's going to cover everything of the lecture material until the last Monday. So basically for the graph lecture specifically, it's going to cover up to and including slide number 42. I think that's the very first 2 slides on the breadth first search. And also for the 4 tutorial materials we have got so far. Okay, and also for your assignment number 1. And I'm going to do the highlights for every part today. Okay. Okay, and then, so just according to your grading scheme, 20%. And you will need to make sure you try to log in for EECS. Don't waste your time really looking for the actual password really on the day of the test, right? Got to make sure they work. So just find a spare lab machine and also give it a try. Closed book, okay. There will be 2 parts. The programming part and also the written part. The programming part is going to be done on Eclipse, and the written part is going to be done on E-class, right? So there will be explicit links for you to download things. So don't worry, it's going to be very clear to you. I will try to see if I can maybe even make the cover page of your test available to you even before maybe early Monday. So you can take a quick look, just 1 page, so you know exactly where you can expect the things to be clicked on. Okay. And for the programming part, just make sure you know you are allowed to actually use array list, hash set, any library classes we actually use in the assignment number 1 solution, but you got to make sure you're familiar with the basic usages of those classes, right? I think whatever library classes we demonstrate, that's all sufficient for you to really use in the actual test. You don't really need anything else than that. So for example, for array list, just know how you can add, remove, create a new list, and how you can get an element from a particular index. That should be sufficient. And also similarly for hash set as well. So when I go over the solution, I will highlight those usages for you. So just take a look at those and make sure you're familiar. Okay. All right, so you got to make sure you export your project as a zip file, which is what you did for assignment number 1. So that should be familiar to you, and there will be a link for you to submit. Okay. And it is recommended you actually try it out, since now we already got a solution to you, so you already know how to do things properly. What you can do, the best preparation for assignment number 1, the best way to prepare for the programming part for test 1 is to go to remote lab, import your assignment number 1 starter into the Eclipse over there, and then try to do it from scratch, right? Maybe or at least do parts of it from scratch, and then compare against the solution. Just practice. And also know how to use debugger. You might actually need it in the actual test. And for the written part, there will be just a link for you to log into eClass, and then you can complete a quiz over there. And make sure you can do the dual mobile, right, on your mobile phone. That's also important. Okay, so this is about answering question, but I will be there. So I will just try to answer your question, but normally I might just ask you to look at the question more carefully. Okay, just let you know. All right, and then other than that, make sure you have your ID. All right, other than that, okay, let's see. So for the programming part, Eclipse, and then you have to study for assignment number 1, and also any of the all the programming exercises in the previous tutorial, right? Especially tree rotation, for example, that we did in week number 4. And then just make sure you actually submit and export your project in time, right? I'll try to give you reminders during the test, but you gotta make sure you really do it, and don't expect to do it in the last minutes. That's usually some of your fellow students actually fail to really submit in time, which is not good, all right? All right, so just about make sure your code will compile, everything you develop should really go to the model package, just like assignment number 1. And make sure there's no compilation error, okay? And submission for grading, similar, all right? All right, and grading criteria. So this is to say you will be given some starter tests, definitely enough for you to get started with. But you have to make sure you program your solution in the most general way possible. You don't really handle just the cases mentioned in the starter test. You have to look at the problem description carefully and handle all the situation, right? So there will be some extra grading tests as well to really assess your solution, but they will be still consistent within what's really set in the problem description. We don't really test you anything that we didn't mention even in the problem description. So that one, you don't need to worry. All right, and then some rationale, take a look if you have any doubts, right? So that's about the programming part. Any question about the programming part, I can clarify first about the test. So today, I can also just show you one more time about how you can import the project into the Eclipse and also export, right? Just make sure everything is clear to you. And then we got written part, right? Primarily, it will be multiple choices in eClass, right? So you guys have done maybe many quizzes in different courses on eClass. So that one there, I don't need to explain. So that's just a standard way of calculating the mark. So when you ask me about is there any negative marking, so just look at the grading scheme over here. It's just eClass default, right? I didn't design that, just default. Okay. There could be some short answer question as well. You might be asked to justify or maybe provide some short answer, maybe for definition, maybe for explanation, or you might be asked to write a single line or several lines of Java code. It's also possible, right? For the eClass, it's possible. All right, so your best way to study would be to really go over the slides and also iPad notes for the written test, for the written part of the test. All right, so that'll be it for the guide. All right. Any questions about what's going to be the format, expectation, etc.? Yeah?
For the test itself, the written and
programming
take place at the same time, right?
They take place at the same time, so you will be given questions for both of them at one go. You can decide which one you want to do.
How much time would you suggest for each section?
It's a very good question. I would say if I were you, right, I would definitely start with the programming part because that one there, there's no way for you to guess the answer, right? So you want to just do it. Okay, I'll write it down. If I have to suggest maybe some strategy, okay? So given that you only got 50 minutes, of course, I will try my best to be sure the amount of question combined together is fair within 50 minutes, all right? But of course, I assume proficiency, right, at the same time, right? Okay, so let's say 50 minutes. Let's say you want to give yourself, let's say about up to 25 minutes just to begin with, up to 25. I can give you guys maybe some reminder when you're reaching the 25 mark. And for this one here, just do the programming part. Okay, by the end of the 25 minutes, so you start with 4:30 p.m. So that means around 4:55. Okay, that's the timing I'm talking about. Around this time over here, you should have at least some partial completion with no compilation error. Partially completed projects with no compilation error. Of course, I'm hoping that it's already fully completed, so you don't have to worry about it. I'm just saying in the worst case, right? With no compilation error, so you don't really have to pay for the penalty, for compilation error. And then from this one here, export and submit. So in the worst case, if you really cannot come back to this part here, at least it's, you have no compilation error, no penalty, and you have submitted something, right? You got a minimum base to be graded, at least. Okay? I would suggest maybe about 25 minutes-ish. But of course, it really depends. If you really believe you just need a few more minutes to complete everything, go with it. That's okay. I'm just saying about 25, all right? So go with this first, and then whatever that remains, you can say maybe the remaining 25 minutes or so. And then you can go for, maybe just go for the E-class, right? Just go for the written test. And for this part here, it's going to be multiple choice. You can strategize about which question you want to really spend time, answering, right? So depending on how many questions there might be, maybe you are able to answer all of them. That's good. But if you really have to choose, at least you can navigate through the question first. So I would suggest maybe on the E-class, you can start the first minute or 30 seconds. Start with the first minutes or so, navigating through the questions. Okay, just to see which one you want to answer, because you can always go back and forth. All right? And then I would say finally, so for the 25 minutes over here, you can try to see if you can leave yourself maybe the final 10 minutes, 5 to 10 minutes. So you can leave the final 5 to 10 minutes. You can use them maybe to check your answer. Or if you want to simply go back to the Eclipse to really finish a little bit more. Okay, that's roughly the plan I will more or less try to devise. But you want to remain flexible. What you really, really want to avoid is to get too stuck into the programming part to say, oh, okay, so I thought I might only go for 25 minutes, but you ended up having 40 minutes there. That's not good. You want to draw a closure, right? Like a temporary pause over there. Maybe 25 minutes. I can definitely give you guys some reminder. Okay. Can I answer your question? Okay, good. Just strategy, right? Yeah. All right. Any other questions? Just about the test format itself. Yeah.
Will we know like the percentage of marks like for each section before?
That may not be something I will reveal beforehand, but I would say maybe tentatively, maybe about half and half, tentatively, around, not exactly like a 50%, right? So you can expect maybe about 50% of the test will be about programming, and maybe 50% will be about written, but it depends. Yeah. Did you have a question? Same question. Okay. Yeah. Okay. Good. Yeah, I think since the test weight is 20%, so I think half and half is about 10% for the course grade for programming part and 10% for the written part. I think that's about right. Okay. Good. And then, okay, so that's about the actual guide for the test. And then let's now move on to the assignment 1. Okay, so that's just the assignment 1 question, right? Why don't we just go to the solution? So guys, I want to take your opinion since you are here, right? So again, assignment number 1 itself simulates the test. It has a programming part, it has a written part. Which part do you want to start with? Programming or written? Diverse opinion, okay? So any preference? I can definitely do both, I'm just saying. How about this? Let me do programming. I'll make sure at least we got enough time for written as well. How about that? Okay. And I would say for the programming part, you guys already got a solution. Okay. What I would do is, how about we just go over, have a linear scan of all the classes and methods at one go, the critical ones. And I will just go over them to tell you what I think will be important for you to review. And then if there's any particular part you want me to put more explanation, I can do that. All right. Let's say we do the programming part. And then we take, after that, we take a short break, and then we do written part, okay? All right, so let's see. Good. All right, I'll make it a little bit larger. Let me, first of all, just start with the package, edge list graph base. So this is the, okay. So this is the package you will be given verbatim during the actual test as well. Okay, so this is something you have to familiarize yourself. You don't have to extend it yourself. You don't have to, just the base. Question?
Are we allowed to? Like, because in my solution, like I added a field inside of vertex.
I would say this, yeah. So don't really touch this particular part here because when we do the grading, we're gonna use this just the original version of all the classes here. If you really have to define any helper method, most likely in the edge list graph class, you can feel free. You can get around with that. Rather than defining in that particular class in the base, you can define it in the actual graph itself, right? That one's okay. You can create as many extra you can create as many extra methods as you like in the class.
It was an extra field I added inside of vertex, not a method, but.
Yeah, so, but you'll see the actual solution. I didn't have to, right? So we want to go with that kind of, version. Yeah. But now that I tell you that, so hopefully you can practice accordingly, right? Yeah. So what I just told you, fellow student, I'll write it down explicitly. So you'll be very, very precise for you. So for your programming part, okay, so no extra class you want to create. No extra class, which is not required by the JUnit test. And also, no modification. No modification on the base, the edge list graph base package classes. However, it is okay to add extra helper methods, as many as you like. Helper and helper methods and attributes. Okay, if there's anything explicitly we do not allow, I'll let you know in the description itself. So just pay attention to the instruction. But in general, you can definitely add more methods and also attributes. For example, in the edge list graph class. Yes?
So I have a separate question, but for test cases given in assignment 1, would you say it covers like all the edge cases that we would need to know?
No, the starter test usually will just give you a good starting point. At least you know how to expect a header for the method and also input and output. It may not cover all the edge cases. So when you actually program, you will want to have those edge cases in your mind. Make sure your methods will cover them.
So this assignment 1 doesn't have all the edge cases?
This assignment, I think is pretty complete, I would say. Yeah, it's maybe I'm missing something, but I think that one is pretty good, especially for depth first search, even though the graph is not that complicated. Okay. Yeah. Mm-hmm. Yeah. So another advice would be, so the starter test may not cover all the edge cases. So you have to make sure to program your method. Generally. Not just hard-coded for any input values. That's my point. All right, so that's like a basic principle. Okay, all right, let's now look at the code. Okay, quickly. All right, so for the vertex, really you just have to, you got an attribute element. That one's pretty good, right? Only one generic parameter. So V here is really the element, the type of the element stored in the vertex. Can be integer, can be character, can be anything, right? And the most important attributes, like what we discussed in the lecture, is this one here, right? It's about the position. All right? And let me tell you that this, let me make the highlights right away. So this is the place to guarantee, so this kind of position, this position makes constant amount of time deletion of vertices possible. Okay? Let me visualize that a little bit right here. Okay? Let me go back here. So roughly speaking, for your graph, you basically have the list of vertices. Let's say vertex list. And that one there is a doubly linked list, right? So doubly linked list conceptually is simply just, okay, of course you got a header and trail. Let me ignore that part of detail, all right? So basically you got, let's say, one here, and another one here, right? Etc. Okay, doubly linked list. Of course, you will link back as well. Right? Doubly linked list. So each one of them is a doubly linked node of vertex of certain type. Okay, each one of them. All right? So that means, for example, so this is a data element field. Oh, let me just put it in the middle. That might be a little bit better. So this will be the data element field, right? So this is the previous, this is the next. And for the data here, it will point to some vertex objects. Okay, vertex of V, let's say. And V can be any concrete type. And now, if you go back to this particular attribute here, right? That one there, we got vertex list position. That one there is of type DL node. What does that mean, right? That's something I didn't explicitly mention in the lecture, but that's something I was hoping that you might kind of at least get used to the complication here. But there's a reason for this extra complication. Okay, let's go back here. So that means you have an attribute right here called the vertex list position. Vertex list position. So this one here simply point back to the node. All right? This is very important, guys. Okay, pay attention here. All right? So now this link here is really what makes the deletion of the vertex efficient. This link over here. So now think about what's going to happen. Okay? Let's see some example code. If I have my edge list graph, let's say this particular vertex has the reference V, let's say, right? If I want to remove some vertex, and then I simply pass V over here. So now, how would it actually happen, right? All you got to do is, you will see the solution is simply just going to say G, which is the graph, the vertex list. Dot remove. And then there's got to be something to be put. Now, what should we put here? So the V itself, okay, guys, you got to see this detail here. That's important. Let me say it again, right? The edge list graph has a list of vertices, which is going to be a doubly linked node of vertices. One of the vertex could be like a vertex here. And the vertex itself has a position pointing back to the node that stores this vertex object, right? It's like a bidirectional link. So now, the question is, when you actually implement this remove vertex, maybe you already got it in your solution. So now, how can I remove this particular vertex without having to go from the beginning of this doubly linked node, go all the way to here and then remove it? Is it possible?
You would use the method get position.
Okay, I'm glad you mentioned that. If you say get position there, it's already big O of n. Oh, you mean the get position there? Okay, sorry. My apology. I misunderstood what you said. Okay, exactly. So that's correct answer, and I'll put it down. Exactly this one here, right? Yes, you're absolutely right. This one here. All right, right here. Get vertex list position. So this guy over here is just going to be v dot get vertex list position. Okay, what that would do is when I give the reference to this particular vertex, I want to remove it. How do I remove it? I simply say, give me the position of that particular vertex, which will give me this particular node in the doubly linked list. In which case, to remove it, I just need this reference here and remove the references around. That's going to be big O of 1. All right? And for this one here, revisit the remove method we discussed explicitly in the lecture. Okay, we did talk about it. All right? And the remove method itself is big O of 1. I would say this is one of the most important details you want to pick up from assignment number 1. Oh, sorry. Sorry. There we go. So this one here, remove. This itself is big O of 1. All right? All right, any question about this detail here? All right. Okay, so let's now move on. And then we got get vertex, yep, similar, okay? So you can set a position, also you can get a toString, right? There's a minor detail here which I also documented in my solution. So in Java, let's say you're trying to look at things like object values in the debugger. So usually if you don't really redefine or override the toString method, it is simply going to show you the address of the objects. So you can see that I try to override the toString method for every class, like a vertex and edge over there. It's because when I needed to debug in the Eclipse, once I override the toString method, I am able to see that, the value. All right, that's why. Okay, it's a practical thing for you to know. It's not exactly required by the JUnit test cases, but it's going to be useful for debugging. Okay, next one. All right, so for the edge class, it's going to be very similar. So it just takes 2 parameters, right? You can think about the V here is really the element type of the origin and destination vertices, right? You can see we got origin and we got destination. Both of them got V, right? They're referring to this V. And the E here is the element type for the edge. So the edge and the vertex do not need to store the same thing. I think what we will see later is the edge is going to store integer to denote the weights of the edges. Especially when we talk about the Dijkstra algorithm for shortest path, that's going to be the case. Okay, that's for later. Okay, and then similarly, we also got something called edge list position, similar. Right? So later on, when we want to remove an edge from the list of edges, it's also going to be big O of 1. All right. So this attribute here also makes the removal of the edges efficient. So this allows big O of 1 edge removal from the edge list graph. All right, and we got a standard constructor accessor mutator, right? And you can also got origin and also destination, right? Very similar. And that's about getting the position, right? Like for the vertex. And also you can set the position as well. And finally, you got the toString. And I said it's already showing vertices, in the debugger. right? So this part, the toString method here, is not strictly necessary because it's not really mentioned in the JUnit test cases, but it could be useful for debugging. All right. All right. Let's now look at the actual graph, right? So the library classes we are using, which I will recommend you try to get familiar with yourself, are the, let me highlight them. You got array list, you got hash map, you got hash set, and also you got list. So these are the different ones, right? So these are very standard library classes, right? So there are really no fancy methods that you should really know about them. Just how to add things, remove things, how can ask if something really exists in the collection, etc., right? So I think just get familiar with them. Okay, let's take a look at the graph. So here we got the basic attributes, just according to the slides. So when you want to implement an edgeless graph, you got vertices, and also you got edges, right? You can see the doubly linked list declaration here just correspond to the visualization right here, right? I just say, well, basically doubly linked list contains the chain of nodes, basically. Okay? And then we got the constructor here, which is initialize empty lists, all right? So when you have to develop from scratch, just make sure you know about at least these two attributes. If you have to add any additional attributes, you can feel free. But I think that these two should be sufficient. Okay, okay, getting the number of vertices, getting the number of edges, they are good. And you may also want to get yourself familiar about what methods are available in the doubly linked list class in the base. Okay, I'll make a note for you, because you'll be given the identical class on the test day. Okay, so here, what methods are there to use? Okay, and then we have get vertices. Okay. So this one here should be very straightforward. So here, one thing I want to mention, which is about iterable. Okay? Iterable is really an interface in Java. So if you return something called iterable, you will be able to use the so-called for each loop. Okay? So let's see this. So let me just give you one example here. Okay? Let's say if I say iterable. And I'm saying vertex, let's say vertex of string, for example. Okay, and then I would say vertex list. And then I say is G graph dot maybe get vertices. Okay, let's talk about how you can use it. Because I say that it's actually of type iterable, okay, what that means is I can now use the vlist as this. Because there's no index in the iterable, right? Which is something for you to iterate through one by one. You can simply say for loop, right? And that loop over there is going to go over the vlist one by one. And I know that every element there is going to be of type vertex. So I can say, put a vertex over here, vertex of string, and then v. And then I can put here vlist, okay? And then I can simply use in the body of the loop, simply just a v. Okay, I can just use a v here. Okay, that's what you will see in the solution. Again, the point is, whenever the return type for the method is iterable, so that means once you get a return type, you will be able to use the for each loop without the indices. The iterable itself has no indices. You can only go over things one after another without the indices. Okay? And how do you return something that's an iterable? Okay? Basically, I believe all the collection classes in Java are itself iterable. So think about iterable as like an interface in Java. But not to think of, it is an interface. So iterable, it's an interface, and then you can think about one of the classes that implements it is the array list. Okay, implements. So that's why you can simply say result here is actually an array list, and you can just return the result. That's okay. You're expecting something that's an iterable. Dynamically, you're just returning array list objects. It's definitely possible, right? That's something we did in 2030. Question? Or?
Could we make it so that the DLL list that we get on the test like actually extends the iterable interface so we don't have to like go through the rigmarole of like making our own array list?
No. Just we'll go with whatever that's there. Okay, yeah. I don't want to make any changes to the base actually right now. So we might just leave the way it is. Yeah. All right. All right, and then you can look at the loop itself, right? That one should be quite straightforward. Just go over the linked list. You know how to do it. Make sure you know how to do this kind of iteration. And then get edges similar. Just go over the list of edges. Right? Go over the link node and get the corresponding elements, which is an edge or vertex. All right, any question so far? So all these stuff might look simple from the solution, but you got to make sure you can do it from scratch. Okay, I think that could be the challenging bit, okay, which I would like to see on Monday. Okay, and then we got other things. Get the degree of. Okay, so let's talk about this one here. Okay, I think I can talk this one in a little bit more detail, because for others, like get incident edges and also get edge between, they're done in a very similar way. Because for the edgeless graph, if you somehow want to find out the edges, it's a little bit trickier, but I'll find out. I'll show to you. I'll just talk about one of them. Okay, this one here. Okay, let's say given some vertex. Okay, so given this particular vertex here, first of all, each vertex has no information about what edges are connected to it. How do I know? If you simply go back to the definition for the vertex itself, right? You can see here, for the vertex class, you only got elements, and also you got vertex position. You have no collection, like how many, what are the collection of edges that's connected to this particular vertex. You don't have the attributes for vertex. That's intentional, right? That's just the strategy for edgeless graph. So how can we figure out all the edges that are connected to this particular vertex? So we got to go with that indirectly. Okay, sorry about that. I'm not sure why it would jump. Okay, right here. So let's now draw something very quickly. Okay, let's say this. If I have a graph like this, let's say I got X, I got Y, and then I got Z. Okay, 3 vertices. And then I got edges. Let me say this is E1, this is E2, right? So the degree of X should be E1 and E2, right? Conceptually, let me tell you the solution right away, but I need to visualize again, also in the runtime structure. For me to figure out that the degree of X is actually 2, I cannot just directly go to the vertex object itself and see what are connected to it. I don't have that information. What I should do instead is to iterate through all the edges one by one. And then for each edge I'm looking at, I want to see either the origin or destination is actually X. If it is the case, increment the count by 1, indirectly. All right, let's see exactly how this can be done. So now, let's now see, we got vertices. Okay, we got 3 of them. Okay, so this one here is pointing to the vertex for x. And this one here is pointing to the vertex, let's say y. And this one here is pointing to the vertex z, right? Also remember, we also got a position, right? This one here points back to here. This one points back to here, and this one points back to here. That's about vertices, straightforward, okay? What about the edge? And also we got edges. We only got 2 edges. So for edges, we got also doubly linked node. Only 2. And this one here is pointing to some edge objects. And this one here is also pointing to some edge objects. And also we know that there will be a field for position pointing back. There also will be a field pointing back to the position, right? So far, so good. Sorry? Oh, the power, right? Thank you. All right. Let's see. Okay. Awesome. And then right here, so we got a position pointing back, and then, so there will be also the origin and destination, right? So now let's see for origin and destination. Origin and destination. For E1 here, let's say this is the origin, that's the destination. So that means origin is going to point to x, and destination is going to point to y. All right? And then for E2 over here, origin is going to point to x, and destination is pointing to z. All right? So now if you want to figure out the degree of x, you basically have to go over the edges list one by one. And for each edge over here, you want to look at either the origin or destination. If one of them is equal to the vertex you're looking for, the degree, then you increment by 1. All right? So now, if you want to figure out the degree of x, in that way, so when you are at this particular edge over here, you can see the origin is x plus 1. All right? And when you go to the second edge over here, you can see the origin is also x. So plus another 1. So degree will be 2. All right? Kind of indirect. The way you figure out incident edges follow exactly the same logic over here. So this is the most critical insight you want to get into about visualizing the edgeless graph. Okay? Also get prepared to be asked maybe several questions on this, maybe in the test. So just understand the layout. Okay? Any questions about this? Okay, so let's now move on a little bit. Okay, so we got, okay, this one will be done in a very similar way. I'll leave that to you. And also this one as well. Okay, you basically should go over the list of edges and find out the answer in a different way. Okay, at vertex, right? Basically at vertex, you can see that we are using the position, right? So the way to, once you use the position, you will be able to actually make it, it's actually big of 1, constant. All right, and also add edge, remove vertex, and also remove edge. They're done in a very similar way. You just have to make sure you use that position, the pointer back to the link node. And once you get to link node, you're basically back to 2101 for removing things from the doubly linked list. Question? Mm-hmm.
Like, incident edges are the edges like incoming to the node, not outgoing.
But this is like an undirected graph.
Okay, so if it's an undirected graph.
Undirected, so that means it's basically just connected to it. it could be either, okay, I see what you mean. It also depends on how we set up the layout of the graph, okay? Let me use that diagram as an example. Okay. Let's say this one here, right? So here, for that particular setup, I say x happens to be the origin, and this one happens to be the destination. I could set up in a different way. I can say when I create edge number 1, I can set this one to be origin and this one to be destination. In that way, you should still consider E1 to be incident on x. X can appear either as the origin or destination in the case of undirected graph.
Okay, so like on the test, can we assume that it's going to be an undirected graph again? Or?
Yes, you can assume. Yes. Since I say it's going to be very similar to the assignment, so let's make it simple. That one I can say, okay? I'll put it down. Also remind myself, right? So when I make questions, I'll remember to put that assumption, okay? So we can assume the graph for the programming part is undirected. Okay, just like A1. Okay, let's keep it that way. All right. All right. The last bit I want to take a look for the programming part. Let's look at the general structure for depth first search. Okay. And then we can take a short break, and then we can still go up to maybe half an hour. You know, if you want to go over the written part, we still have some time. Okay. All right, so for the depth first search, it's actually done in a way that simply corresponds to how we do the tracing for depth first search in class, right? So here, we don't really have a library class called stack. Maybe we do, I'm not too sure. So here you got basically, let's see the variables you need, right? So this is just a sample solution, which simply corresponds to how we did things in the class. But if you did it, for example, recursively, that's okay. I just chose to do it iteratively, because that way we can see more explicitly how things can be done, you know, also manually. So, but just make sure you also understand this solution here, because that one there simply corresponds to how we did things in the class. Let's look at the variable first. So we have visited. Okay, we keep track of all the nodes that are visited, which is a hash set. And also we got a hash map over here. Okay, let me highlight a different way. This is going to be return value. Hash map is going to mark edges, right? It's going to go from edge into Boolean. Okay, conceptually, you can think about it's more like this. Think about it's more like a set, and then each set has a pair. Maybe edge number 1 happened to be a discovery edge, in which case I'll say true. And also for edge number 2, happens to be a back edge, for example, and then I'll say false, etc. Right? It's going to be a set of pairs. So you definitely have to look into how to use a hash map. But I think the usages we kind of demonstrated in the assignment should be enough. All right, and then we simply use an array list right here for the stack purpose. Okay, and then we simply just keep adding, you know, element to the stack, right? So that one you can definitely look at the correspondence, right? So now you want to pay attention to the exit condition right here, right? So here we say that as soon as the stack becomes empty, that means the DFS terminates. When the stack is empty. All right. And then we try to look at different stuff. You definitely want to get all the incident edges. Okay. Get all the incident edges and visit them one by one. Incident edges and visit them one by one. And I simply store them into IE list. Okay. And then let's see here. this is to say, let me just review the steps right here. You can also double check on the tracing, okay? So given an edge, if the edge is already marked, you just skip it, right? It has not been marked, it's been already marked either as discovery or as the back edge. You don't need to visit them anymore, all right? If the edge is unmarked, and you have to look at two cases. Either if it leads to unvisited vertex. So that means it should be a discovery edge, right? Otherwise, it should be a back edge because it leads to something that's already visited, right? Kind of straightforward stuff, okay? So you can study the code structure itself, right? It's kind of boring to really repeat it. Just look at the actual implementation and just make sure you know how to do things. Okay? Is there any particular part for the depth first search you want me to go over? Were you okay? Okay. Okay. Another part you also want to make sure you review. Okay, I want to put it here. Also, make sure you review the starter test. By starting from different vertex to start your DFS, can the markings of edges be different? Yes, actually, but you got to find out in the starter test. Of edges be different. All right, that's an important review question for you. Okay, so take a look at the starter test cases for the several test cases for depth first search, and then look into them. Right, so you definitely have to know how to read the test cases. Any questions? You don't need to. You know, just pose a question for everybody to think about. You don't need to. But if you want to share the answer with everybody, that's okay too. Go ahead.
So yeah, it does matter. Like,
it does matter, right? Say it a bit so everybody can hear.
Yes, it does matter like which vertex you start at, because that will change like which discovery edge, which edges are marked as discovery and which ones are marked as back edges.
Yeah. So we're thinking. Yeah, exactly.
I feel like it's easy to see when you like look at an example.
Yeah, of course. You know, but now we just talk about intuitively, right? For a concrete example, you can look at the starter test.
Yeah.
So
you made a comment in the test cases saying like assume that we start from vertex A.
I think I said something like that, right? Yeah. So basically, if you start with a different vertex, the incident edges you're looking at might be different. In which case, you're starting the edges in different order. In that case, you're going to mark them differently. That's intuitively. So guys, please review that part, all right? All right, I would suggest we take a short break, and then when we come back, we still got about 20 minutes, 30 minutes, we can look at the written part, okay? All right, I just noticed that I forgot to actually show you guys one more time just about import and export, you know, just so I can record it for everybody to also look at. Let me do it very quickly, just 1 minute. So you will actually get a chance, you will be given some download link during the test. So let me just download the starter, okay, let's say, for your projects. Let's say you're gonna click on some download link during the test, and let's say save it on the desktop somewhere, all right? And then you're gonna launch the Eclipse on the server. It's already here, okay? I'll just show you again how to import, okay? You basically gotta say File, and then import, right? That's something you did for your assignments, right? And under General, you gotta go to Existing Projects into Workspace. Next. And then you gotta say, not this one here, but you gotta say Select Archive File. And then you're gonna browse to wherever you kind of downloaded the file. Could be, for example, on the desktop, and then the starter, all right? And then you're gonna say Finish. So that will be imported to your workspace right here, right? So you gotta develop your JUnit, gotta develop your model package there accordingly. Now, how do you export for submission? You gotta right click on that, the projects, and then you're gonna say export. Under general, and then choose archive file, and then next. And then over here, you're gonna browse to, could be desktop and you give a name. You know, whatever name it is, you'll be on the instruction. And then save it on the desktop and then choose that one for submission. All right, so make sure you don't really waste any time on this, right? I just want to mention to you. Awesome. Okay, let's look at the written part quickly. Okay. Bye-bye. Okay, so let me look at the proof maybe later. Let me look at maybe this part here. So, guys, are you okay with this kind of a question here? That for search? Okay. Okay, so basically just gotta make sure you practice, and then I find that maybe you want to be very systematic, you know, when you do things. I would suggest when you do this one here, right? Of course, here I say the starting vertex could be A. I could have asked you to say maybe the starting vertex now become I, in which case you have to do it accordingly. So if you want to generate some practice question yourself with your study mates, you may want to think about, what if I start the depth first search from a different vertex, maybe I, instead of A, right? That's one possibility you can try. And then when you kind of do this depth first search, right? I would say you want to keep track of several things at the same time, simultaneously. It's very, very confusing if you simply say, oh, what I have done so far, and then go back to figure out exactly the order. It's going to be too late, right? You're going to just lose track. So let's say I start with A. Every time if I say I go with one edge right here, right? Because I go alphabetic, so I go to B. As soon as I do this, I should really, first of all, mark the sequence, number one. And then B here is going to be a new vertex. So I'm going to push the B into here. And then I will mark it down right here. So I'm going to maintain a table here, maybe on your sketch paper, to really see whenever you push something into the stack, you're going to keep pushing them, right? And then every time, if you got a particular vertex, for example, if you have visited all the edges already, in that case, you're going to pop it off. In that case, let's say if you pop it off from the stack, you also have to mention that in the actual table as well, right? So I want to say you want to keep track of all these at the same time, right? Are you okay with that for search? Yeah, question.
Just a question about on node G, when we went from G to G and then we went from G to J as like the discovered edge.
Uh-huh.
Is there a reason why we didn't go to check like C first? And like when we did this package, because I see the order, it goes 4 and 5, and then like, of course later down the line, then it checks the back edge that is from G to C. But if we're going in like the most alphabetical order, is there like a rule that I'm missing there?
I can look into this, but I believe that's just the order I follow. Okay, you're basically asking.
Yeah.
Okay, so I can make notes. I need to look at that because yeah. Are you asking about right here versus this?
Yeah.
Okay, can I just look into this, and then I can get back to you. If that turned out to be a mistake, I'll definitely fix it. But I doubt it. But I maybe, yeah.
I just want to check. Like,
Yeah, sure. I can double check. Yeah, no problem. I'll double check myself too. Yeah. All right. But overall, the process you're gonna follow will be what we did in the class. All right. All right, so if there's no further question about that first search, you guys can just keep practicing. Maybe you can try to gather several people together, and then you can try it out, maybe starting with a different vertex for that first search. I think that could be a nice practice for you to try. All right. Okay, apart from this, let's take a look at the proof. So that's mathematical induction. So I try to lay out in the most structured way. So you definitely want to, first of all, talk about strategy. For each one of them, you're going to prove by mathematical induction, but on what? The first one there is going to be on the number of vertices right here. And the second one here, which is slightly more challenging, is really on the value of k, about how many edges you want to remove from the actual graph. All right, so each proof is going to maybe require a different value to really prove the mathematical induction on. So you really want to decide. Okay, but you still got two examples here. Okay, so this one here is actually very similar to what we kind of said in the class. So I just want to visualize some of it a little bit just for you. Okay, just take a look. But of course, you have to really follow through the equation itself, right? This kind of stuff will be the most effective. Will be most effective. You have to study that carefully yourself to really find out the details. Okay. So here for this one here, if you look at the the inductive hypothesis, right here. So to really visualize it, let's see here. So here, let's say we have some cloud over here. So we're saying this is a tree, right? And the tree has certain property guaranteed by the assumed inductive hypothesis. We don't know the exact shape of the tree, but we do know some property that's enough for us to really extend the tree by one node and then prove again the property, right? So here we say the number of edges will be simply, number of vertices will be simply n. So number of vertices is simply equal to n, and we know that it's also k. And it's larger than or equal to 4, at least 4, since we already proved 1, 2, and 3 in the base cases. Okay, we know at least 4 nodes, 4 vertices. And then we also know that about this particular property, okay? The degree of all the vertices is going to be exactly 2 times k minus 1, okay? So we also know about this property, all right? So now what we want to do is we want to create another tree. We want to create just another tree right here, okay? Let's say we are adding a node called x. The only way is to, I said A, right? Okay, let me be consistent. Actually, let me say this. Choose some vertex A from here, some existing vertex A, and then you want to create a new node called B. And then you are basically connecting them. So this way, you can create a strictly larger tree with exactly k plus 1 vertices, okay? So this one here, after adding the edge, so this is a tree with k plus 1 vertices. Okay, so that's the main visualization. Okay, basically once you actually got this one understood, I think you can actually figure out the equation there. Okay, that's the first one. The second one, I would say for the second problem here, seems to be more challenging, but I would say the most important part for you to understand is this part here. Okay, I'll highlight it. This case, this k equal to 1. Let's try to understand what's going on here. Okay, just right here. Oh, sorry, let me do a little bit better. Right here. Okay, let me make it bigger. So here, what we are saying is we are trying to remove one edge from a connected graph, right? So let's see how we can visualize this. So there are two cases over here. So just in case you haven't seen the solution just yet, so now we can go over just these two cases. And these two cases will be actually referred to in the later inductive case. Okay, let's look at that. So we are saying that we are removing one edge from a graph G. Okay, let's say, for example, let's say this is our graph. So we are removing one edge from a connected graph. First of all, let's give one concrete example about what a connected graph could be, right? Just make a simple example. A, B, C, and then let's say that. let's compare this. Let me give you two versions. This is one. This is another one. Let me just erase it right here. Would you agree? Both graphs are connected, right? The only difference is the left-hand side is connected and cyclic. It has a cycle. The other one is connected but acyclic. I'll write it down. This one here is connected and also cyclic. And this one here is connected acyclic. All right, right here. And now, question for you. If I say I remove, well, just before I remove anything, how many connected components are there in each graph? How many connected components? One, right? So here, there's only one connected component. And here is only one, right? You may have to revisit the definition for connected component. Okay, for each one of them is one, all right? And now here's a question. If I remove the edge A and B, if I remove this edge between A and B, am I going to have the same resulting connected components in each case? Okay, so that's really the case number 1 and 2 for you. All right, so here, if in this case, I remove this edge, how many connected components do I have? Still one, because somehow A and B is connectable, not just by this, but also by that. So if I only remove this one here, they're still connected. All right? So guys, this is a very important insight for you to really know. Okay? So number of connected components remains to be 1. On the other hand, in this case over here, between A and B, this is the only one that's going to connect them. If I remove the only connection, the number of connected component becomes 2. All right. So that means whenever you're trying to remove a single edge from a connected graph or from the graph, how many connected components can you increment? You can increment maximum 1. All right. So that's a critical insight into this proof over here. So I would say when you go over this proof, you really want to make sure you are convinced about this particular case over here. I mean, this particular base case, which explained about case number 1 and case number 2, right? And later on, we also refer to these 2 cases as well, and everything will flow. Okay? Questions? All right.
Test or midterm about the base case.
Mm-hmm.
Do we have to have multiple base cases?
Okay. I see what you mean. So typically, I think that there's not really like a magic number about how many like an example you should really do for base case, right? So if I do want you to prove about the base cases, for example, I'll be very explicit about how many you will need. Mm-hmm.
Okay.
Yeah. So, but somehow for your assignment, I want to give you just several. So I give you at least 2, right, just for you to see. But I think you typically will need at least 2 to really see some critical insights into the general pattern. For example, here, if I only do k is equal to 0, in that case, I wouldn't be able to see that case 1 and case 2 pattern. So I had to just increase the k value to 1. In that case, I can see case 1 and case 2. And then I do another larger k value here for base case, so I will be able to also apply that to reaffirm my observation. So I'm pretty confident about the pattern I observe from the base cases, so now I can go ahead for the inductive case. So I would say at least 2. At least 2. And then you'll be even better to go to 3. Yeah. All right. Guys, we're going? We're good? All right. Okay, good luck. And then I'll release the recording. And then my final tip. So go over, of course, go over everything, lecture slide, iPad notes. And then for the programming part, I would say I'm not going to give you anything that's more difficult than the assignments. Of course, it's going to be shorter, right? I will definitely keep the time limits in mind, but you got to make sure import, export, submit. You got to make sure you understand the process. And also for the basics about the edge list graph, make sure you understand them. And also go over the solution. And then, yeah, that should prepare you well. All right, thank you. And I'll release the recording later. Okay.